So first, I'll start off with a quick background on NLP with transformers. You know, what do transformers change for NLP? Go through some of the pain points that we've heard coming out of this adoption of transformers in the NLP space. Talk through some of the prior solutions in research and academia that have come out to solve these pain points. And then we're going to walk through our research that improves on these solutions. We'll walk through additionally how you can apply our research to your own use cases, to your own data, and fit it into your pipelines. And then we'll close off with closing remarks, future work, and an open discussion. So any questions coming in, feel free to go ahead and put them into the Q&A and chat. We'll answer them as long as they come in towards the end, as well as anything that comes up during the discussion. And there was actually a quick question that just came in, which was, do we support remote work or only in Boston? So we do actually have a hybrid workforce. We have some people that are completely remote, some people that are coming into the office, a few days a week, and some people that are in the office almost every day. So hybrid workforce, and yeah, more than happy to bring on remote employees. We have several on the team right now. So thank you for that question. All right. So let's go ahead and dive into the background. So specifically, well, just kind of, at a high level, NLP is everywhere, right? A lot of our communications are going back and forth through text, right? Whether it's, communicating through messages, communicating through social, or just documenting the work that we're doing. There's a lot of just kind of human interactions that are encoded in text and that can be made into actionable information to help businesses and to help people in general. So going through these, we have token and text classification. This can be anything from named entity recognition to sentiment analysis. For example, diving into so for example, Pepsi, looking at Pepsi, and if they want to look at how they're trending as a brand overall on Twitter, they can use a sentiment analysis model to just constantly stream out any tweets that are tagging them or mentioning them, and then get the general trend of sentiment as a positive or negative towards a brand in real time, especially, and make actionable information as ads come out or marketing campaigns come out. Additionally, we have question and answering, there's information retrieval, all kinds of different use cases that are popping up. The other thing to call out is NLP is sequence-based. So the traditional route for sequences was to use RNNs. Obviously, the problem with RNNs is that they can have long training times. They can be very unstable in training, and they can't be parallelized across these sequences. So it makes it very hard to deploy and to train. Transformers enabled parallelization with attention, right? So we can take a certain set of sequences, and then the attention layers can come in and relate which sequences are actually important to each other, right? Which words are important to be able to extract meaning from text. And this significantly improved training and inference times because now we can actually parallelize, we can do batches, and this helps both on, as I said, on the deployment and on the training side. The other thing is that NLP is a very large field with many distinct tasks. So overall, this means that a lot of applications actually have a shortage of data. There are common data sets that we work with, even on the research side, that have as few as 500 samples in them, right? So it's very easy to overfit to those. And to be able to solve that, BERT came out. And what BERT did is it first learns language constructs by doing something called mass language modeling. So it uses unstructured and unlabeled text, and then just predicts what word should happen in a sentence, right? It masks out a certain word, like the cat is brown. It'll mask out cat, and then it'll ask the model to try and fill in that word. And after that's done, and after it understands language, then we can fine tune to both small and large data sets. And BERT was able to set the state of the art for being able to do this, and actually significantly moved the needle forward in that. Given all the good things on BERT, let's go ahead and talk over some of the pain points. And one of the big ones is the expense. So BERT is expensive to deploy. The file size is close to 500 megabytes. And in addition to that, we have 40 millisecond inference on an 8-core CPU. So this is a batch size 1, sequence length 128. 40 milliseconds is a long time to be able to call out and spend on an NLP model, especially with how much text generally you have to process in these text pipelines and for business applications. So research and industry has attempted many modifications to BERT, specifically to decrease storage and memory size, as well as to increase its inference performance. And generally, these have broken down into compression techniques. So looking through these, we have architecture modifications, such as structure pruning. So this is where we'll remove the number of layers. BERT has 12 layers in it, so we can remove the number of layers. So we can remove half of them to go down to a 6-layer architecture, or we can decrease the width of this model and the hidden state within it. And both of those are considered structural modifications on the architecture. Additionally, with that, a lot of people are doing distillation. We'll go through distillation later as well. This is a general process of taking a teacher model, so a very large teacher model, and rather than with your small models, your small compressed model, rather than just training that on your loss function for your data set, you're going to use the teacher to generate what the teacher's outputs should be, thinks it should be, and then the student and the smaller compressed model tries to match to those teacher outputs. And this has worked very well for NLP. Additionally, there's quantization, where we'll go from an FP32 representation of the model down to an int8 representation, right? So dropping down 4x in both weight storage as well as activations. And then finally, unstructured pruning, where we'll go through the model and remove unused connections within that. And we'll go through all of these as we talk through. But let me go ahead and actually pause here before we start diving into the research. We had a quick poll that we wanted to put out and see if see what kind of use cases everyone is using. So Sasha, do you want to go ahead and try and open it up real fast? Perfect. All right, so hopefully everybody just got a poll that just popped up on their screen. Go ahead and fill that in. And if you'd like, but this is mainly just for us, so that we know, generally what we should be targeting for use cases, and we'll share out the information that we actually get from these polls, as we've done in the past, back out to the community. So let that go for another 10 seconds, and then we can dive back in and dive through the research.
I wonder if can attendees see the poll? Can you? Like poll results, I mean, can you see the poll results? If not, we should just quickly cover the mark.
Yeah, definitely.
Oh, it says not yet. Maybe when that, thanks, Colin. Okay, well, last call, how about 5 more seconds? I'm gonna end the poll, and then maybe you will be able to see it. I don't know. Okay, I'm ending the poll right now. Hey, Colin, can you see the results right now? Or Malek? You can start talk. Oh, nothing so far. Okay, you can talk about the mark if you want.
Okay. Well, actually, I cannot see them either. So, Sasha, if you have them, can you go through?
Yeah, I can. So there was a lot of, I'll just keep it to the top 3. So from the use cases that you saw on the poll, the top 3 were text classification at 58%, sentiment analysis at 54%, and question answering at 50%. So all of those 3 are above 50, which is pretty interesting, because all the other ones are below 38 and below. So there is definitely a heavy emphasis on question answering, text classification, and sentiment analysis. Were those the first 3? I wonder if people are just clicking the first 3. I don't know, I forget. Anyways, go on, Mark.
Awesome. All right, thanks, Sasha. So yeah, so let's go ahead and dive through some of the prior research that has happened on compressing BERT. So one of them is distill BERT, where the idea was we could take structured pruning and combine it with distillation, as talked about before, where we have a teacher model and a student, and distill BERT just gets rid of half the layers in BERT, and then uses distillation to try and converge to a better model than what it would on its own, right? So smaller model compressed, and we're going to distill the knowledge from that larger BERT model into distill BERT. I removed roughly 50% of the params, gave about a 2x increase in performance, and got to 97% of the baseline F1 score on squad. So 97% recovery based on the BERT, the original BERT 12 layer. So really, really good, right? We didn't cut out half the params and then therefore lose half of our performance. We got pretty close to the original. Another one that's come out is tiny BERT, where it was improved structure pruning and improved distillation. So normally with distillation, we'll do it just on the outputs. TinyBERT was actually distilling multiple pathways throughout the model and its hidden state between the teacher and the student. And this allowed it to actually converge to a better solution. So we'll go through a little bit of comparisons later, but the most compressed version of TinyBERT removed 85% of the params, gave 9.4x increase in performance, and got to 93% of recovery on squat. So significant reduction in the original BERT model, and still, maintaining a very usable model. And then finally, just talk over quantized BERTs. So generally, whenever you're quantizing, we'll get to 75% reduction in parameter size, going from FP32 down to NT8, about a 2 to 3x increase in performance. It depends on the implementation for this, and pretty much always we get full recovery, at least whenever we're doing quantization or training. So with all the NLP models that we've seen and all the research, NLP seems to be very, very good with quantization, at least down to NT8, and be able to get full recovery. And this is generally perpendicular to the other compression techniques. So all the structured pruning, unstructured pruning, we can just apply quantization on top of these and be able to get the benefits of quantization along with the other compression techniques. And then let's go and dive into prior research specifically on pruning BERT, on unstructured pruning. So whenever we say pruning, we have a dense model here where it has all the connections between our nodes and our neural network. And then whenever we prune, we're going to remove a lot of the connections in between. So one of them on BERT was the lottery ticket hypothesis. And this is an extension of the lottery ticket, which came out a few years back. It was very, very popular, but I was trying to apply the same techniques to BERT. And they use magnitude-based pruning, which is a zeroth order method. Essentially, all that we're doing is we're looking at the weights and the magnitudes of the weights across the entire network, and then getting rid of the smallest ones. And this generally works out pretty well to say that the smallest weights are not important to the loss function or to the network, right? As we train, weights that are not important to our loss function get regularized towards zero, and therefore don't have an impact on our loss. And what they did is they pruned while pre-training. So on that mass language modeling task, they pruned the BERT model, and then they kept the sparsity mask intact, and then they sparse transferred onto all of the downstreams. And with this, they're able to remove about 60% of the parameters with 99% recovery. So 60% is pretty good, but as we've seen, there are other techniques that can get pretty close to that as well. Another one that came out a little bit after that was movement pruning. And this was adaptive sparsity by fine tuning. So what it did is it was pruning based on the magnitude and the gradient. So it was using first order information. So the gradients that were flowing back based on our loss function, it was combining that with the magnitudes to generally see the trend of where the weights were moving. If the weights were moving towards zero, it would remove those. And if the weights were moving away from zero, it would keep those. And this one, this time they were pruning while fine tuning with distillation. So they would take the BERT pre-trained model, fine tune it for a little bit on a downstream task like squad, and then they would begin pruning on top of squad while it was still fine tuning. With this, they were able to remove about 70% of the parameters with 99% recovery. And these are essentially the two kind of top papers that have come out on pruning BERT. So let's go ahead and talk over how we improved on top of those. Well, one thing is 60 to 70% sparsity is low, at least in our experience on the computer vision side. Whereas at 50, we can prune that to 90% with 99% recovery. So then the question is 90% sparsity achievable for BERT? Is it achievable in the NLP domain? Is computer vision and image classification something special that that 90% is achievable there, where it doesn't actually transfer across domains? Well, as we were able to discover, yes. So we were able to improve on the training processes and also use second order pruning methods to be able to enable 90% sparsity with recovery. So the first part is just even with magnitude pruning, based on what the lottery ticket hypothesis did, we were able to improve those processes and go from 60% up to 85% of params with 99% recovery, right? So getting rid of 85% of that network, at least the weights in that network. And then finally, we introduced fast wood fisher. So this is a second order method. And with that, we were able to remove 90% of the params with 99% recovery. So we were actually able to get to the parallels that we've seen in other domains. Specifically with wood fisher, what we're doing is looking at the loss function and looking at if we apply a mask and we essentially remove one weight at a time, how much is that weight going to affect the loss function? And in this way, we can get really, really granular details to be able to say, one, which weights are the least important based on the active loss function that we're training on. And two, it actually gives us information how to update the weights afterwards. So after we prune, then we can update and continue training and doing the iterative process. And with that, we're able to get to 90% sparsity with 99% recovery. And then the other question for us was, does it work on the pre-training with sparse transfer? And the same processes do. So we're able to take 90% sparse BERT and transfer it to 99% recovery based on dense baseline. And after all this, we were able to apply this into the deep sparse engine and get 4.5x speed up, right? So looking back at still BERT where it had 2x speed up, this is keeping all 12 layers within BERT and pruning out the redundancies within that network. And we're able to actually get over double what the still BERT was able to do just with pruning alone. And then there was a quick question that came in for what is the impact of second order pruning methods on training time? That's a great question. In terms of pruning, actually what's interesting is that it reduces your overall training time while pruning, mainly because you're able to prune in fewer epochs. So with the magnitude approaches, we would take about 30 epochs on downstream pruning to converge, but with the second order Fastwood Fisher, we're able to do all this in 10 epochs. So one thing is that it actually ends up being faster than magnitude pruning, even though it is more expensive. And then to the specific question, with Fastwood Fisher and the second order method, it does take a little bit to do the steps, but these steps are actually, we only do about, I'm trying to do the math in my head, I would say about 20 steps over the entire pruning process. So the impact of it actually doesn't end up being that much on the training time. Each step does take a little bit of time, a few minutes to calculate, but those steps only happen about 20 times over the course of training. So it actually doesn't impact the training too much. Yeah, great question. And so here's a visualization of what this actually turns out to be. Here's our second order pruning methods up here. Our baseline here, as you can see. And then here was the movement pruning paper. And then the sparse BERT and the lottery ticket papers, right? As you can see, we're able to get to 90% actually with perfect recovery on the baseline, whereas movement pruning and these other methods were not able to. So now let's talk about how we can compound that pruning research with the other techniques like structured pruning. So can we combine the improvements with the smaller models? So what we'll start off with is we'll remove half the layers from BERT, right, to get down to 6 layers remaining, which is roughly equivalent to still BERT architecture. Pruning to 80% gives 99% recovery for the 6 layer, and it beats the still BERT and tiny BERT, the larger tiny BERT model. And this gives 6.4x speed up with deep sparse. We can then say, well, what happens if we remove 3/4 of the layers from BERT? So we go down to a 3-layer BERT. And then we prune 90%. Well, that gives us 93% recovery, which actually beats the tiny BERT, the smaller tiny BERT model. And all of this with 14.8x speed up within deep sparse. So let's go and visualize these results. So as I said, less than 6 layers where we're at the tiny BERT 4-layer and our 3-layer model. You can see that we beat it in terms of F1 on squad, but we get 14.8x speed up over the top of the 9.4x that the tiny BERT, the smaller tiny BERT model was able to get. To still BERT and tiny BERT 6, we're able to get 2x over the top of the BERT base, while we were able to get 6.4x speed up using our methods, using a 6-layer 80% prune model. And then finally, if we look at 12-layer, we have the BERT base where we can do a 12-layer 80% prune model that gets 3.4x speed up and beats out prune BERT and gets very close to the recovery on the BERT based model. So overall, these are really, we were really happy with these results, and it was a lot of work that went into it. But what does this mean? Well, one thing is, what does it mean to add quantization on top of these results now? So one thing we want to call out whenever we're adding quantization with deep sparse is that we're working with a VNI instruction set since we're on CPUs, and that requires us pruning in blocks of 4. What this means is that it because we're adding structure to our pruning, a little bit of structure to our pruning, it lowers the sparsity we're able to get to by about 10% for the same recovery. One more note on that. So for example, our 90% models that we're recovering, to do block 4 pruning in block 4, we would drop down to 80%. This gives us a 10x improvement in performance for 99% recovery whenever we're looking at our 12-layer, 80% sparse quantized model. And then we can get up to 30x performance at a tiny BERT accuracy, where we're looking at 3-layer BERT, 80% pruned with distillation, and then using quantization alert training. So let's look at these results. What's really, really surprising about this is that we can actually get to GPU level performance on latency with just a 4-core MacBook. So likely what you're logged into right now, we can actually get to a GPU level performance on that setup. So we can see here is the T4 GPU has about 13.9 millisecond latency for a BERT base running at FP16. Our 4-core CPU implementation is able to get to 11.8. A V100 GPU is able to get to 7.8 milliseconds. And then our implementation with the sparse quantize is able to get 7.4 on an 8-core server. So we're actually able to beat GPUs on latency with BERT, with 12-layer BERT model, with all getting to 99 within 99% of the same accuracy. And now let's go ahead and take a look at the results in action, just a quick video to show this. So what we're doing is we're interested to see what would happen if we ran searches for crypto across Twitter. So we look for hashtag crypto, and then we want to see what the results would be. As you can see, sparse quantize is running much faster than the dense BERT on the left. And this is all on the same CPU setup. And overall, we came out with 75% negative on crypto. So definitely matching up with the trends that we've been seeing a little bit in the crypto community. All right. And then, so let's go ahead and dive into a quick demo. So all of our models and our research is open source and pushed up and free to use. And I'm just going to go through a quick demo to show off that. So let me clear my terminal out. So all that you need to do to be able to replicate this is do pip install deep sparse. I already have it installed on this machine, but it'll go through and install it. And then what we're going to do is run a quick benchmark for that sentiment analysis model. That sentiment analysis model that we were running on the crypto tweets. We're going to go ahead and run a quick benchmark on that. All right, so what this is doing is it's pulling down actually the baseline model, the dense 12 layer. So this is FP32 baseline, not pruned at all, just so we can establish what our general performance is without any optimizations. So what I've done is passed in we call them stubs, zoo stub for the model, and deep sparse is going to create that, and it's going to run a benchmark on that using asynchronous mode. So we'll let that complete real fast. It'll run for 10 seconds. There we go. So we got a throughput of about 73 items per second. Now let's go ahead and change that out for our 12-layer pruned to 80 quant model. So this, again, a same model gets to 99% recovery of the BERT base. And we've just gone through, pruned it to 80% with blocks of 4, and then quantized it. So let's go ahead and kick off that benchmark. Again, deep sparse is going to compile the model. It's doing a lot of optimizations. So it takes a little bit of time, but once it's compiled, that model is free to use, and you're able to inference against it as many times as you'd like. So wait for that to spin up real fast, and then begin benchmarking. So it's going to do the same exact benchmark. It'll do an async measurement where we're just throwing multiple streams at it at batch size 1, and it's going to run that for 10 seconds. And the big number to look at once that finishes is what happens to our throughput. So before we were at 73 items per second, and we want to see what we come out to with this setup. And while we're waiting on that, just a little bit of background. I'm running on an AWS C5 12x large instance. So this is a 24-core instance. So it'll get a little bit better performance than what you'd get if you're running it locally. But yeah, overall, let's see where this one comes out.
And Mark, we have a QA coming in asking about semantic search.
Okay, great. Thanks, Ben. So I'll get to that in a second. But yeah, so we're able to get to almost 500 items per second with just pruning and quantization. Again, 99% recovery over the top of that 73 item per second baseline. For semantic search, we do not have anything on this yet. This is actually one of the really exciting areas that we're pushing into now and starting to explore. So stay tuned for that as we push our research into that. We're hoping to get some things in probably the next few weeks into the next few months and start releasing so we can do that. But yeah, definitely very interested in semantic search. And if you have if you have any preferences on repos that you'd like to see us use, then feel free to send them over, and we'd be more than happy to take a look. We're actually in the discovery phase on that right now to figure out which repos we should be integrating with to be able to power our research on top of it. All right, perfect. And then let me do just one more quick demo. I'm going to spin up a Python shell. And what I'm going to do is I'm going to use the deep sparse Python APIs to be able to perform a sentiment analysis setup. So what I'm doing is deep sparse.transformers, importing the pipeline. So we are fully integrated with transformers and built on top of their pipelines, so that we can work with any kind of pipeline that's plugged up and on top of Hugging Face already. And then what I'm going to do is go ahead and construct a new pipeline. I'm going to tell it that it's the text classification task. And then we're going to pull down that same model that we just benchmarked, right? The sentiment analysis model. So we're going to create a pipeline for that. Once that pipeline's created, then we're ready to invoke it with data. So we'll let that spin up. Deep Sparse has to compile again, use all of the algorithms to be able to get the best performance. And once it's compiled, we're ready to go. And then another quick question that came in while we're waiting on that. What are the areas and projects anyone, especially specialized with data science, can collaborate with Neural Magic? Yeah, so all of our research is pushed out in open source under our SparseML repo. Currently, we've been pushing a lot into image classification, object detection, a little bit in image segmentation, and now into NLP. So we're more than happy to collaborate across anything. Actually, if there are specific integrations that you'd like to see or specific algorithms that you'd like to see implemented for sparsification, then feel free to send them over or begin a chat either in our Slack or even just open up a pull request on SparseML or deep sparse. So yeah, I mean, there are quite a few different areas and I guess kind of coming back to the core question, there are quite a few different areas that we'd like to collaborate on. And pretty much if it's interesting to you, it's probably interesting to us and interesting to the community. Yeah. Awesome. And then, so now that it's compiled, let's go ahead and just run a sample inference through this. So what I'm going to do is just grab the sentiment response from the pipeline of this food tastes great. So something that's very positive and hopefully comes back positive. So you can see that came back almost instantaneously. And that's because, again, going back to what we were running earlier, we're running very, very fast for latency now. Let's go and print this out. So yes, it is very confident that that text is positive. All right, perfect. And then we have a few more questions coming in. So we have one that says which hardware is best for BERT. This is generally at least using the deep sparse engine. Anything with a x86 architecture, so AMD chips, Intel chips, that's what we're designed to work with right now. We're looking at ARM in the future and actually working on that currently. So in the next few months, we hope to have something out for ARM. But anything on x86 that's a newer x86 architecture should be able to work. The minimum is instruction sets or AVX2 to be able to run. And then if you can get on Intel with VNNI, that'll give the best performance. And then another question that just came in, can we deploy TinyBERT on Raspberry Pi 4? So this is going to be dependent on when we get ARM support. So this will be, probably a few months out right now. But once we have ARM support, then that would definitely open up Raspberry Pi for running in deep sparse and be able to get performance for that. And then just going through a few more questions that came up. All right, so another quick question on wondering how our results scale. So what specifically I was looking at for large models like BERT large or Roberta large, and smaller models like TinyBERT and MiniLM, how our results scale with those. So actually, we're going to be publishing BERT large results in a little bit. It actually scales very, very well as we grow the compute. So BERT large is even more compute intensive, and as we prune away as we remove the compute by pruning from that network, it actually gets significant speed up. So stay tuned for those results. We're going to be pushing those out in actually the next week or two, and very, very excited to have that out. But it actually scales. We were able to get to 90% with full recovery on BERT large, and significantly better speed up than what we were able to get even on BERT. Towards TinyBERT and MiniLM, this is actually, MiniLM is actually something that we're spinning up on now as well. We're really excited to take a look into it. We expect it to scale just about as well as what happened on our 3-layer. So we'd expect over top of MiniLM, anywhere from a 6x speed up to a 10x. And honestly, it depends on the batch size and other configurations. But we're going to be actively looking into MiniLM next. And we'll have more results in the near future on that one as well. All right, so let me go ahead and go back to the presentation. There are a few more questions coming in, but we can go ahead and go through those towards the end because we're almost done. We can open up to even more discussion. So the final piece is how you can apply our research. Well, I shouldn't say final, but next piece is how you can apply our research. So one thing is checking out our paper on arXiv. So we publish all these results under the optimal BERT surgeon. Here's a link. We'll be sharing out the slides after, so you can grab these links. Another is the Twitter sentiment analysis demo, the video that we ran. Go ahead and try that out. We have that open source ready to go. You should be able to check that out and begin running immediately with that. Additionally, visit our use case pages to get started with your own data. So this walks through use cases of how to train, how to benchmark, how to deploy from our sparse models, either all using sparse transfer learning, so that it's very easy to transfer onto your data and begin giving you performance increases on your deployments. So go and check those out. We have question answering in there, text classification and token classification examples all ready to go. And then finally, join our community to ask questions and stay current. We have Slack and GitHub and quite a few other channels, so feel free to join in on those. And then finally, just future work before we go into discussion. So, stay tuned for more future work from us. As I was going through, we have quite a bit coming up, but all of it essentially centers around more deep learning models and use cases. So we want to get more accurate models with better distillation and compression methods. This is specifically towards the MiniLM conversation. And then, in terms of use cases, we're looking at information retrieval, summarization, translation, segmentation, and more on top of that. But these are the next places that we're looking into. Towards that question of semantic search, information retrieval is next on our list. And let us know if any other use cases or models you'd like to see us work on. We're very, very focused on community and very focused on pushing our research out to that community and be able to grow that. So let's go ahead and jump into the rest of the Q&A. So another question was, will you apply these sparsification methods to speech field? Specifically calling out that transformer-based ASR models are very popular. So this isn't something that we've looked at yet in depth, but yeah, if you'd like us to take a look, feel free to share over a repo that you're actively using, and we can take a look at what the integration would look like for that and get it onto our roadmap. And then additionally, what are places NeuralMagic offerings could benefit or provide value to any AI-based startup? So would love to, and then just goes into, would love to learn about any real world case studies on impact, this had to business. So we're actively working with design partners right now. And overall, the big things revolve around, well, two use cases. If you're within deep learning. So if you're actively deploying deep learning right now, we're either working to improve your latency so you can get back to the user faster, or decrease the cost to run deep learning, right? So you don't need an expensive GPU, or you don't need to ship the data off to a GPU farm. You can ship it off to a local server or run it on the local device next to where that data is, and be able to both save in time and in cost. Stay tuned on diving in with specific case studies, because those are what we're actively working on right now. But overall, our goal is to be able to empower more companies and more people to be able to deploy deep learning by significantly reducing the costs and by reducing the hardware that's needed to be able to do that, right? Be able to deploy it anywhere on commodity CPUs that you already have. All right, awesome. These were all really great questions that came in. Let's see, we have another one that just came in. How much work is required in terms of time and human effort if I have to reduce latency in our current computer vision pipeline we have? So this is what we're actively working on. It depends on what you're doing with computer vision. We're trying to expand out all the models that we support, so that it's as easy as sparse transfer learning. So you just have to plug in your data set and get some results on top of it. If we don't have the model that you're actively using, then let us know, and we'll get it onto, get it prioritized onto our product roadmap, or we can sync up with you and talk over what that timeline would look like. Getting into the core of the question, sparse transfer learning with that will just be a training run across your data set, so a retraining run across your data set, so generally pretty cheap in terms of time and human effort. If it's a new model, then this is research that we're actively working on right now on how to build out what we call recipes, which encode all the hyperparameters around sparsification and the algorithms that we use, so that so we can make it as easy as possible. Generally, it should work out to be pretty limited in terms of human effort. To be able to do this, you'll just have to create a recipe, and it'll mainly be on machine time. So retraining the model so you can get convergence and get better performance. But awesome, all very good questions. I'm just going to leave it open for a little bit longer to see if there are any other questions that come in.
Hey, Mark, Sasha here. The Raspberry Pi question, I know that DeepSparse, we're working on making DeepSparse work on Raspberry Pi on our roadmap. But isn't there? I remember talking to somebody before about using sparse ML to still optimize the model and reduce the footprint, so they're more optimal for Raspberry Pi deployments. Is there anything around there?
Yeah. Thanks for bringing that up, Sasha. So yeah, using our models and using sparse ML to be able to train those models and fit that in with your pipeline. Those can all work as is right now. You won't be able to get the benefit, the inference speedup benefit that we quote in DeepSparse currently on ARM, but you can definitely get the model size reduction benefits and also the quantization benefits by using sparse ML, and be able to plug that into your pipeline so that it will work with what you're using to deploy right now on Raspberry Pi, whether it's through a Jetson Nano that's hooked in, or another inference engine. Yeah, great point, Sasha. All right. I don't see any other questions coming in. So that's it for everything that I had to run through. Sasha, was there anything else that you wanted to close out with?
I think Valentin just sent a question in. Do we have a Python API to use our server package? I think that's a yes, Mark, right?
Oh, perfect. Yeah, we do. So we have both a Python API for the server package, as well as a command line that you can just spin up. So you can do deepsparse.server. Actually, I can probably pull that up real fast. Give me 1 second. So there's a Python API for that. And then additionally, we have a CLI that you can just run straight from the terminal once you install DeepSparse. So let me grab a sample command for that real fast. And so what I'm going to do is do deepsparse.server. tell it that I want to do text classification, and then just give it the model that I want to run with text classification. And what this is going to do is it's going to spin up a server that's ready to go. It's built on top of Fast API, and it's going to spin this up so that you now have an HTTP inference or an HTTP setup so that you can make requests into it. And there's a doc setup so that you can actually do sample inferences, but otherwise you can just pass curls into it to test it out. This is going to spin up the dsparse.server. And otherwise, to the question, there's a Python API that exists in under DeepSparse as well. If you will, we can send out the documentation on that in the follow-up as well to call out the DeepSparse server. Yes, great question. Oh, I seem to have lost my Q&A.
So a few more
there we
coming
go.
in. Yeah.
Yep, perfect. And then next question is it possible to get inference speed up for sequence-to-sequence models? It depends on what type of sequence-to-sequence you're running. If it's RNNs and LSTMs and things like that, we don't currently support those under DeepSparse. But you know, if you're doing transformers on top of sequences or anything like that, then yes, those are actively supported. But we don't have anything for RNN based support yet. And then another question that came in: have you compared throughput when running the model in single-thread mode with one replica for each core? So that's a great question. So kind of getting at the core of multiprocessing scaling. So as we scale up across multiple cores, it's not a perfect linear relationship. You know, going up 24 cores isn't going to get you 24 times the performance of one core. So this is actually something that we have actively been looking at. The one issue that we run into whenever you do one replica per core is that you're actually going to be colliding on the cache, the L3 cache. So it is going to slow those down. There actually is a AMD blog that we put out recently where AMD has a unique architecture where it has shared L3 cache across, I believe it was 8 cores individually. And what we did was actually program DeepSparse in so that it would spin up one inference on each of those 8 cores so that it would make full utilization of that L3 cache. To be able to reduce memory transfer times within the model and be able to execute faster. And in that way, we're actually able to get significantly better performance than just trying to use all, I think, 128 cores that were on, or maybe it was somewhere around, I think it was 128 cores that were on it. So that is one case where you can get significantly better throughput, but one replica per each core is going to be very taxing on the L3 cache. So generally that isn't going to scale as well. And then another question that came in: since your methods require further training, do you have an approach for very large models? For example, GPT-2 and 3. So this is a great question. This is at the core of the research of where we want to go to next, which is reducing the amount of training time that it takes to be able to converge to a solution as much as possible, getting as close to one shot as we can. So this is something that we're actively looking into. We are evaluating GPT-2 and 3 currently as well. These are a little bit lower on our priority, mainly because we haven't had too many asks from a business use cases for it. But it's definitely on our list, and it's active research that we're looking into. The pieces of fast wood fisher, and second order pruning algorithms. Whenever I mentioned that we're able to actually update the weights based on the loss function, this actually gets much closer towards one shot, right? So we're able to prune out a significant amount of weights and then actually update the remaining weights to make up for the weights that were removed without retraining. It's not perfect yet. You definitely still lose accuracy whenever you get into the higher sparsity levels. But going to image classification example on ResNet 50, I believe we were able to get to 60% sparsity one shot without losing any accuracy. So this is active research that we're working on to try and see how we can tackle these larger models, especially as you said with long training times. Yeah, great question.